talk, and this is some recent work that I've been doing with Anindo, Oprotin, and there is a continuation of this work that Joe Penendon is also there, and maybe Discover will also join. That's one thing, and this question marks at the end are for me, because I have a lot to understand as of yet. So I don't get Polyakov's details. And so I'll apologize at the beginning if I can't answer a few questions. But of course, Anindo will come in the next round. So the brief outline of this talk is to first to calculate the critical exponents from the epsilon expansion, and then there is a usual way of story using the QFT, and then it's not been too long since Rishkov and one of the students, Long Ming Tang, were able to derive the same epsilon expansion using the conformal OPE way of doing things in the in the interacting fixed point. And of course, while I will say that this new way is quite elegant, but it can only give you up to some particular order in epsilon, not up to the full epsilon expansion and so on. But using this, so apart from that, there has been also some critical exponents that has been gathered, the information about the critical exponents that has been gathered numerically using the conformal bootstrap, and that is for this ON models in 3D. So Poland, Simon Duffin, and all these people are actually working in that. This is it's a non-perturbative numerical approach, and they have found some very good agreements with existing experimental results. And what we are trying to do is to understand this epsilon expansion, the critical exponents from the epsilon expansion from a seminal work of Polyakov. He did that like 40 years back. That was in 1973. Where he used some basic ingredients such as using the time-ordered correlator and building out the unitary and crossing symmetry 4-point correlator, and then using algebraic constraints to determine the anomalous dimensions of certain operators in the field. And at the end, we'll see that we do get the same results from all these approaches. So whether it is from the QFT, whether it is from Rishkov's approach or from Polyakov's approach, so all of these yield the same results. So this is the usual way of calculating the critical exponents in the epsilon expansion. Suppose you take a ON vector model with a phi for interaction, that's a critical model. And then what you do is you first we'll find using RG flow that there is Wilson-Fisher fixed point where they'll be satisfied by some. So this is up to one loop, beta function, and lambda is the coupling constant for the interaction. And from that you will find that at the Wilson-Fisher fixed point there is a non-trivial value of lambda for which the function vanishes. And there are some successes.
Where is named in your?
No, so this is for, I did the beta function for this scalar phi for theory. So yeah,
N is
yeah. So n is actually 1. Yeah. There is no n here, but this n can come, and it will come. And at the Wilson-Fisher fixed point, you will find that you can write the normalized coupling in terms of some expansion series in epsilon. By the way, we are working in, so D is actually 4 minus epsilon, from which I started the theory, and then I moved to the interacting fixed point, which is a Wilson-Fisher fixed point. So then you calculate the correlation function that is supposed to give you the mass correction, so basically corrections to the conformal dimensions of fields in lambda under this RG flow from the free or Gaussian fixed point to the interacting fixed point. And then you, of course, write down this whatever anomalous dimensions or corrections to the conformal dimensions of these operators in terms of an series in epsilon, and that's what we call the epsilon expansion. And so this way has been, so this is a very elegant way of seeing the things. Insofar as quantum field theory, what we generally do is we calculate loops of some order, then we calculate the beta function. So basically this is the one loop beta function, you can go to the next order and so on. And then you obviously get some corrections to this factor and you get an epsilon expansion for this, and this is very established. So people like Wilson, Fisher, Ford all have worked extensively on this. But recently, so that I was saying, Rishkov and one of the students came up with some. So what I mean by the question marks after this a new way is that this was not like unknown before, but it was actually put to use in a very elegant fashion. So the calculations of loops and all simplifies a little bit in this approach. So what people find is actually the Wilson-Fisher fixed point is a conformal invariant fixed point, and then Rishkov would tell you that you consider certain axioms. So first you put forward some axioms for your computation. One of the axioms is that for any operator in the Wilson-Fisher fixed point, if you take this epsilon goes to 0, it should actually tend to this free operator. And the second axiom is actually a continuation of the first one, which tells you that any endpoint correlation of these operators at the Wilson-Fisher fixed point, again, if you take this limit epsilon tends to 0, it will go to the endpoint correlation of free fields for the theory. But there is some kind of ambiguity here, because if I take the free field theory in 4 minus epsilon dimension, and then I take the epsilon going to 0 limit, so then these two conditions are trivially satisfied. So we need, so then we should tell you that we need one more axiom to get what we want, and this is the multiplicity combination. And what precisely is going on is that if you take into account the interactions of your, say, some critical line models or something. By the way, for this stuff, I will concentrate just on the critical line models with some hyper interaction. Then you see that there's an equation of motion which relates the fundamental field phi I with some other field phi I into phi square. And this equation of motion actually tells you that, so in previously when this lambda was 0, this phi I, this phi square phi I, and all these things were primary operators. But now, if you go to the interacting fixed point, then this phi square phi I will become a descendant of this fundamental field phi I. And so what you find is that if you take this field phi I at the Wilson-Fisher fixed point, that can be given equivalently by, so you don't have an independent conformal multiplet of both the phi I and phi square phi I, because they are related to each other in this through the equation of motion, like we call it. And then one has become the descendant of the other. So it's actually a single conformal ODE, not like two conformal ODEs of two distinct primes.
Doesn't this contradict the first condition? Like limit of the Wilson-Fisher operator should be the free operator.
Yeah, but I haven't told you how this OP coefficients behave. So in ideally, what you should find is that if you take this limit of epsilon going to 0, this thing should again become a primary. Right?
So we are saying phi I free is some field in the Wilson-Fisher, in the 3 minus epsilon case. 4 minus epsilon.
No, I'm saying that the phi I at the Wilson-Fisher fixed point is a combination of these two multiplets, and then they have different coefficients. And if I want to set this condition into action, then this thing should again be like some free field. So this thing should again separate out into two distinct conformal multiplets, not like join into two distinct conformal multiplets. And that you will see how it happens. So this is one thing.
Maybe a remark here that the conformal group has two kinds of representations: generic representations and short representations.
Yes.
And so we can take a limit of a generic representation such that it splits into a long representation and a short representation. And this happens completely continuously. So that's what's happening here.
Yes.
The one representation is split into two, and that's possible because the free representation is short representation.
Yeah, so basically it's recall, that's what explains by like Shiraz said, the joining of two short representations.
Actually, one short and one long.
Yeah, one short and one. So this is one thing, and so I'll fix some notation. This is in what Rishkov has done in his paper, and this notation is that if I'll take capital phi of 2p as phi squared raised to the power p, that's some operator, and then there's this kind of operator with some index I, and these have their corresponding Wilson-Fisher operators which look like so. The Wilson-Fisher operator corresponding to this phi of 2p is w of 2p, and then similarly for phi I of 2p. So that's the notation.
Sorry, I didn't understand what the W's are.
So the W's are the operators at the Wilson-Fisher fixed point. So I'm not representing them by phi's anymore. I'm just because I'll consider two different sets of OPs. So basically, we will get confused. So that's the thing. Now the idea is, so you consider two different OPs. So one of them is for the free fields, where I precisely know what these functions are. These functions are some. So there are actually I have written like. So I have written phi 2p, or I could have written another set of OP which is f 2p. And then phi I of 2p plus 1 phi 2p plus 2. This will be given by f of 2p plus 1 rho of 2p. So where these f coefficients f and rho are whatever those appearing in the.
Actually, I haven't understood. What are these equations?
So this is for two sets. Like one is which for this p is even, and one is which for p equal to 1.
So what are f's?
Oh, so
I haven't understood at all. What phi I and these two operators?
Yes.
Their primaries. What are the right hand side?
So right hand side is that one. So it can be written as this. Isn't it duster? So I can write them as f.
Are you doing an OP?
Yes.
I see.
Yes.
F is the coefficient.
Yes. So that's what I was saying. That the free field OP, and then for free field OP, I have two distinct parts for which one is p is even, and then for.
And what is rho? Rho p.
So rho is the coefficient where you have this phi 3 is phi squared phi I. So I said two different kinds of OP will combine into a single OP, right?
Yeah.
So first I want to take the free field analog of that, then I will take the Wilson-Fisher analog of that. Within the Wilson-Fisher analog, I've written the OP. So these are the Wilson-Fisher operators at the Wilson-Fisher fixed point.
I'm really sorry, I'm just not understanding. Well, these phi's are quite complicated operators. Why do you have only two terms on the right hand side?
So because I'm only interested in looking at the multiplets which recombine. So if you go back to the previous slide, so this is the with phi of 1, I put p equal to 0, right?
Okay.
So phi 1 of I is phi I.
Yes.
This is the free field.
Yes.
And then phi squared phi I is the phi I of 3. So here he put p equal to 1.
Yes.
Right?
Yes.
There are obviously other kinds of primaries and all these kinds of things that you're saying. But the multiplet recombination is between these two specific conformal multiplets. Right? So on the free field side, I am also taking these two conformal multiplets.
Wait, so you're saying it's considering a subclass of
Yes.
looking at some specific.
Yes. Because that is what will give me the multiplet recombination. Other terms as it stands, they will be primaries in the interacting field theory, interacting fixed point, as well as in the free field. So that is what I'm doing. I'm just interested in the part.
There are all the other terms.
Yeah. There are all the other terms.
Reversing languages.
Exactly. So that I have not taken into account because I just want to focus on this phenomenon. What is going on? So on the other hand, in the Wilson-Fisher OPE, so this goes the free field part. On the other hand, the Wilson-Fisher OPE, now I have taken into account the fact that they are related to each other by some equation of motion. So basically I will write this. So W3 is the analog of phi squared phi I, and W1 of I is the analog of phi I. Right? Now, so del squared phi I equal to lambda phi squared phi I. At the Wilson-Fisher fixed point, I will just replace this by these corresponding operators. So lambda squared W3, Wi of 1 lambda. So basically you see that in the Wilson-Fisher fixed point, you can just write the OP in terms of this. The only thing that will be different is this kind of coefficients. This Q3, Q2, Q1 and so on. And obviously by conformal symmetry you know what these coefficients are. Right? So these are completely fixed in the conformal field theory. Okay, so then what the idea is, you take these two kinds of correlators, the 3-point functions. So the essence of Rishkov's idea is that to get the leading coefficients of the anomalous dimensions, you just need to calculate the 3-point functions. That's it. Nothing else. And that's what he has done. He has calculated the 3-point functions of this operator with W1i and then this operator. So for W1i, you can see that this is very trivial. So I will take W2p, Wi 2p plus 1, W1i. On the left hand side, this will be equal to some function times W1i, 1i. And then you can, from the OP, you can again see that W2p, Wi plus 1, W3i will be related to some function times the 2-point function of W1i, W3i. And then for W3i, I will use the equation of motion, this. That's what I'm going to use. And by using this, is one of the conditions that in the epsilon going to 0 limit, this should actually go to the free field 3-point functions. So first, so let me just rephrase. So let me just say it once again. So first you take the 3-point functions at the Wilson-Fisher fixed point. They will be given in terms of these OP coefficients and so on, which you know from conformal symmetry. And then you say that, okay, fine, in this epsilon going to 0 limit, they should go over to the 3-point functions of the corresponding field operators, because that was one of the conditions. And in this, you will get two different constraints. One of them is a very trivial constraint. It only says that if tilde that appears here at the Wilson-Fisher fixed point is the same as the if p that appears here in the free field OP. The other constraint that comes from comparing the operator, that comes from comparing the 3-point function with W3i and then taking it to the phi 3i limit. So the second set of 3-point functions, that is actually what provides us with this anomalous dimensions to the leading order of phi 2p and phi I 2p plus 1. And I missed one thing. It also gives you the anomalous dimension for phi I. So gamma, phi I, it actually gives me at what order it starts from. So it determines this one. So that's the idea.
I'm sorry.
Yeah.
W3i was what was?
So
Phi.
yeah. So W3i was the analog of this.
Phi square.
Yes.
And if you took W on the right hand side, if you just kept that term, W3i. You say it's not even an independent operator. It's not even a primary operator in the interacting theory.
Yes.
So that thing there is a descendant.
Yes.
Okay. So that's just determined by conformal.
Yes. I'm just going to replace. So let me just write it down. Phi 1 of I, phi 3 of I will be given as 1 over lambda phi 1 of I box. That's it.
Yeah. So you say on the right hand side there's only one piece of data.
Yes.
Which is this F2p.
Yeah.
In the free theory it looked like there were two pieces of.
Yes. Yes.
And then you will match.
Yes. Yes. Exactly. And then you match both the points, like you were asking that whether it goes to the free field theory. So this is actually the part that will impose the constraints on the anomalous dimensions by demanding that this second part of the 3-point function actually goes to the free theory, where I know these 3-point functions if I just take the OP here. That's what I am giving, not anything very complicated.
And how are these Q1, Q2, Q3 all fixed?
Sorry, how are these Q1, Q2, Q3 all fixed? Yeah, so you just take the 3-point function here.
Derivative, essentially derivative.
Yeah, you just take this conformal elements and you expand. Right? So you consider 3-point functions. So I'm just taking this generic 3-point function, so phi A, phi B and phi C, that is given by x minus y to the power delta A plus delta B minus delta C, and then for y minus z and for z minus x, these are some powers. So this is x, y and z, right? And then you say that x, y is much less than z. That's it. Then you see that, and then you match with these coefficients, right? So you know the 2-point function, and then you just determine Q1, Q2.
Fancy way of saying it, they're all descendants of the same
Exactly.
property.
Exactly.
So conformal representation.
Right.
Okay, good. That's just a fancy way of saying it.
Yes. So okay, so this is one thing, and obviously I can also determine this. And again, as I stressed, this approach cannot give you anything more than the leading anomalous dimension, because there is caveat. There is a flaw in this. I mean, there is a limitation to this approach, not a flaw. A limitation to this approach. It can only give you this epsilon square term for the phi I and the leading epsilon terms for these higher operators.
You'll explain that?
Yeah. So I think I'll explain that now. So this is not very difficult to see. So suppose you can ask the question. So this is, I have expanded up to so the structure is not changing, right? So this structure, so as far as the multiple recombination is considered, so these are the two chains that will take part in the program. And this structure is not changing. So basically since the W3I is just a descendant of W1I, you can just expand this up to higher order. So suppose if I want to take x mu, x alpha, x beta, then 4 derivatives, right? Or I can take x to the power 4, x to the power 4. Then you can show by explicit computation that the epsilon dependence of this Q1, Q2, and Q3 coefficients for this other thing. So suppose I take this alpha 1, alpha 2, right? So you can actually show that the whatever. So suppose Q1, Q2, Q3. Suppose begins at order epsilon, then you will be able to show that these coefficients also begin at order epsilon. But if I wanted to match with the higher orders in epsilon, I would like to get a series from this constraint as a constraint which can be solved order by order in epsilon. That I am not getting just by using this approach. And the reason is that whatever thing you do, if you just expand to higher operators higher order coefficients in this Wilson-Fisher fixed point OP, the epsilon dependence of all those coefficients do not change.
I haven't understood in detail, but are you basically saying that all you know is one limit?
Yes.
So then how can you get too much information?
Exactly. Yeah. So that is the limitation of this. Yeah. So that is one thing. So first, what one can do is one can see how this lambda square coefficients actually depend on the anomalous dimension of this operator's phi I. And to do that, what you need to do is just compute del square phi I times del square phi I, and then use the equation of motion with interaction. So if you use the equation of motion with interaction, then the right hand side is given by this.
Yeah, now I'm getting confused. I thought phi was for the free.
Yeah. So I think I will put that in a more form. So suppose if you take box of omega 1 I equal to some g of omega 3 I, right? So this is just so I copied too much from this first paper. Then box of omega 1 I times box of omega 1 I equal to g squared omega 3 I. Okay. So let's call it g.
Correct.
Right? Then you take the both sides. Right? Oh.
Sorry, Manju, I forgot to switch back to the slides. Please tell me if you need things switched. Sometimes okay.
So that is what I'm doing here, right?
Yes.
At the final step, it's like
what? Where you on the board? Sorry.
We have the slide,
so they have some problems.
You like to stay on the board always?
They just muted their microphone.
You've muted your microphone.
yeah, we have a slide on our laptop.
So you prefer to stay on the board always? Okay, great. Thanks.
So this is the final thing that I'm saying. So I'm saying that under this So the equation that I have written there is this epsilon going to 0 limit version of this.
Okay.
Right? And then you take epsilon going to 0 version, and then you see that the lambda appearing on the right hand side is related to the anomalous dimension of this fundamental operators phi n. And again, like you were saying, that where is the n coming from? The n is coming from actually here, because there are some combinatorics involved. And then you can, so this equation it should be actually this one.
Sorry, I didn't quite get
Yeah.
it. How did you get that equation? Lambda equal to 4 sigma blah blah.
So this one, sigma is nothing very different. Sigma is just either plus minus 1. These are the constraints that are equals later.
Alright.
So basically these are two roots,
Okay.
right? And then you just do, so what we're just doing is that you just so w1 of I, w1 of I is 1 over x minus y to the power 2 delta 1, where I have written so delta, so the anomalous, so the conformal dimension of w1 of I is actually
The left hand side has a dimension, the corrected dimension of phi.
yeah.
So he tilde expands that in epsilon.
Yeah, so that's what I'm.
And then he compares the first
yes.
Right hand side is compared
the
as
first
state theory.
Yeah,
Right.
So
So I'm writing this delta 1 as delta 5 plus some anomalous dimension.
Got it.
That's it.
Got it.
And then I'm putting the free field value of the delta 5.
Mhm.
That's the thing that I'm doing.
So the only thing that's right hand side is free field, left hand side is arbitrary 2-point function but with dimension correct.
Yes, yes.
And then you assume the dimensions corrected order lambda square and
Yes,
the
yes.
directions.
I'm just assuming that there is some anomalous dimension.
Right.
That's it. The fact that it is order epsilon square will also be coming from the next consistency condition.
So that relates lambda to the anomalous dimension.
Right.
Yeah,
And
the fact that it's lambda epsilon squared, that I can see more or less, because if it was epsilon, if the correction was 1 plus epsilon kind of thing,
yeah, so then you were saying
then on the
that
left hand side there will be an order epsilon.
Right.
On the right hand side, lambda square is already epsilon square. So the correction
Yes.
can only be epsilon square. on
Yes,
the- to
but-
the anomalous.
yeah, but what if so for argument's sake, let's say what would happen if gamma 1 is epsilon cube? For argument's sake.
So that would also be a contradiction, presumably,
Yes.
because you have a left hand side.
Exactly.
Right.
Right.
That implies exactly.
Yeah.
So this forces you to have gamma equal to epsilon square.
Right, but yeah, that is fine. But as it appears that from the 3-point function that I have just mentioned, the second one, where the 3-point function is actually so this is actually W2P. Sorry, I'm just interchanging all these indices. It actually goes to right? This consistency condition will actually force your, again, I mean apart from the arguments here that there is a contradiction and all, this condition will actually force you for the fact that gamma of phi at least is order of epsilon. And the consistency condition here is, one of them is this one. So again, I have just written the free fields. So actually this thing should be box of W3I goes to lambda times 1I goes to lambda times epsilon phi. So that gives me actually this constraint on this, where these are all the corrected parts. So this is just as match the dimensions of the operators on both sides. That is one. Yes, she does more job. And then one of this, and the third the consistency condition is this epsilon equals to limit of this correlator that goes over to the free field correlator. That will actually tell you that lambda times Q3 is rho n, where rho n has some specific form, and these we know already the coefficients of Q3. So the other coefficients are not really.
What was Q3? Please?
Yeah, so Q3 was the coefficient of, so there is W2P, Wi 2P plus 1 has the multiplier which is F2P, x to the power minus 4P is 1 plus Q1 mu. So this is the coefficient. actually you can show once you have calculated Q1, Q2 and Q3 that as epsilon goes to 0, these coefficients will go to 0. Q1, Q2 go to 0, so epsilon goes to 0, even for with lambda. But what happens is that the third term survives in this expansion, so actually it gives you the constant at lambda of Q3, where rho n is this rho to the rho 2p coefficient here, and you have just put p equal to either by 2, well this is valid for both surfaces, and this n is for the ON. And we all know from the 3-point functions in the field theory, we all know what if 2p and rho 2p and rho 2 plus 1 is. So that is the third consistency condition that arrives. That comes from this thing. And then we will assume that the same thing that Sridhar was saying, that I will assume that this is for the free field. So I is not the imaginary I, is the ith operator. For example, if it is so phi squared I, then it should be 3 times delta by 2. Delta is d minus 2 by 2. And for d, I will write as 4 minus epsilon.
So in particular, the left-hand side, that thing should go to 0 as lambda, as the dimension goes to the free field dimension.
Which one? This one?
Right. So you're saying on the right-hand side, we should get lambda times something.
At this point, yeah, so right. So at this point, I'm just
just to understand, the right-hand side is the phi I3.
Yes.
That comes with a lambda.
No, that's a free field. That will come only with a rho n.
So sorry. So suppose I replace the left-hand side as Wi3 by del squared of
yes,
del squared of Wi.
Yes.
Then that should go to 0 as your dimension goes to the free field dimension.
Right, but then that will be augmented by some power of lambda as well.
Correct. It should go to 0 like that.
Exactly. So that's, yeah, you're right. And then that I will augment it by some power of lambda, so that the entire thing is finite.
Because that's how you actually compute Wi3, right?
Right.
Wi3 if it was actually del squared.
Yes. Ultimately, in my final step, I'll put that, and I've already actually put that information. Yeah, and that's right. And again, I just said this I is not, it's not imaginary.
So let me ask another question. So if I go back to the documentation, then
yes.
you're saying that I should think of this only as valid to the leading order of epsilon,
yes,
and not as a power series in epsilon. Exactly why not? I mean,
no. When you can consider it as a power series in epsilon.
Yes.
Because gamma 1. So when I'm writing this delta 1, yes, right? Delta 1 can be written as delta 5 plus some expansion in epsilon, right?
Yes.
But I'm saying that you won't be able to determine the higher order terms in epsilon.
But there will be some constraints coming from the fact that if this equation is true,
yeah,
then the right hand side has only epsilon squared,
right,
and the left hand side has all kinds of powers of epsilon.
Yes.
So therefore, clearly it will give you some constraint.
Yes.
Among the coefficient, the series expansion that you have written at the end.
Here.
Right.
Yeah, it will give, but
okay,
it will just give that.
And you won't be able to determine.
Exactly.
Okay.
Exactly.
Right.
So I'm just talking about the fact where I can get some n dependent on numerical values or stuff. I mean, you're completely right. I can write this lambda as some lambda m times epsilon to the power m, right?
Yeah.
And then I can write this gamma 1 as y1 comma m times epsilon to the power m. And then you are saying that by equating the two sides, I should be able to relate this.
Epsilon cube, epsilon 4
Exactly.
clearly should be 0.
But this equation, should we take this equation so literally?
That's what I'm asking. Should I push it to higher orders in epsilon or not?
I don't think so. Right? I think quantum corrected. The equation
Yeah,
is supposed to
exactly.
get quantum corrections.
Good point.
So basically, we're saying that I have taken this term.
Yes. These are considered equations of motion. So they will get
Corrections. So the leading order is okay. Anything else is unnecessary.
So you can't push it. You shouldn't really push it.
Yeah. So then you will be forced to see that I have just written del square of phi I equal to lambda times phi I. And then you will say that if I had to go to this, suppose say 2 loops, then in the equation of motion I should also include the one loop effect.
Right.
So this del square of phi I should be some
So it's the right hand side should also be corrected.
Exactly.
And then it's
correct, but you don't know the right hand side.
I don't know the right hand side.
At the leading order, shouldn't they just start considering the one loop diagrams in this case? Instead of saying that.
I think at leading order, it's just classical.
Yes.
It gives you the right answer. The first correction will be one loop without the higher order.
So what will be the correspondence between this loop and this epsilon's expansion? I don't know.
It's just a direct transfer. Because in the Wilson-Fisher fixed point, epsilon fixes the particles.
Right.
So the epsilon square will be the two loop effect and all.
Yeah, so basically when you are taking so suppose that order lambda, so basically this is like this. This is order epsilon. And then one loop will be lambda square, which is like epsilon square. Yes. So after you do all this, you define all these expansions, then
There's something that I should know better. Suppose I just took a time. I'll ask you later.
So just from using this consistency condition, we will arrive at some equation for this leading order coefficient. Again, I will stress on the fact that these are leading order because Shira has already said that if you want to go beyond this equation of motion, which is del square times phi I equal to some lambda times the descendants, then you have to take into account the modular correction. I'm not going to do that. So at the leading order, we will get some consistency conditions. So we will get some equations. So let me just So you will get some equations for the nth operator. So I will be like n plus 1 and then n, and this will be either some phi squared to the power n or phi squared to the power n phi I and so on. That's what signifies that y is n plus 1 or y n. These are the anomalous dimensions of these kinds of operators. And once you have located these equations coming from this consistency condition, you can actually show with not much difficulty.
Wait, actually, so what was the output of either that equating that?
Which one?
What is this y and I didn't understand.
So yes. So okay, let's run. So output of equating that is some lambda times the coefficient Q3 goes to some constant rho n. Right? These things you know. And this also you know from conformal invariance.
And rho n came from the left hand side?
Yes. So rho n came from the this part.
Right.
So right? Yeah. So this you know. This is just independent of any lambda or something. This is a number which is some combinatorial factors in n. And this you know. This Q3 coming from this x square times del. Oh, sorry. So this is not del 2. This is del square.
And why isn't there also an f tilde 2p on the left hand side?
So basically, f tilde 2p has already been equated to each other.
From the first free value.
Yes, free value. Yeah, you will force to take the free value.
Yeah.
Right at the leading order. So this you know as a function of gamma 1, and this you know.
Yeah.
Right. So you just put in the values of delta n equal to n times delta by 2 plus the anomalous dimensions gamma n. Right. Lambda you know in terms of gamma 1, the exact expression. Right. And then for gamma n, you say that this is an epsilon expansion which looks like n equal to 1 to infinity in principle, which should be like y n comma m epsilon to the power x. In principle, we are just talking about leading order, so you need not take it as a series expansion, but taking into account that there.
No. Then you should only talk about the first few terms in this series, right?
Yeah. I'm just writing
in
it.
the first two terms. In this
Yes.
Because you are already using f equal to f tilde.
Right.
Which
So actually, it will be just the first term.
Only first.
Yeah, only the first term. That's
So
right.
your n is actually 1.
So m.
Yeah.
M. Yeah. So that's what I've written. So n is always 1.
Sorry, what was n then?
So n is this delta I. So this is y I comma m. So I will write it down. So gamma of n.
So the output is to relate all anomalous dimensions, to obtain all anomalous dimensions as function of gamma 1.
Yes.
Is that
Yes.
right?
Yes.
Okay.
And then you will just obtain gamma 1 as well.
Okay.
And in the last step, when you obtain gamma 1, so one of the crucial, one of the interesting thing is this, right? So that will give you the relation with this. And this 2, rho 1 and rho 2 is 1 for rho 2p and then 1 for rho 2p plus 1. The two distinct set of p's. That's it. Yeah, so you are right. That's just the leading term and not even the epsilon square term, because obviously you are not supposed to take that.
So this n was Guichet's operator, is that right? This n level is...
Oh, so n is, so either phi squared n or phi squared n phi I. That's it.
But I don't know. Now you've got answers without some gamma 1. Well, how do you get gamma 1?
So the gamma 1 you are actually getting by, sorry. So first you solve this equation, right? And then this will tell you that y3, 1 minus y. So you take delta
This is
3
why is epsilon not the anomalous dimension?
delta 1. Right?
Epsilon times that y is the anomalous dimension. So epsilon then goes into the right hand side.
Yes.
And that is, some part of that is the gamma 1. So because gamma 1 has a structure of epsilon divided by n plus something. Right? So you have to read off, because he's taken off that epsilon part. That's why.
Yeah, I'm just already in the epsilon expansion. So I've just ripped off epsilon from both the sides.
But so before this step, you didn't know gamma. You just knew gamma 1 in terms of gamma. There was some relationship between that.
And then I use this equation to find this left hand side.
And you're saying this equation is powerful enough both to determine all the yi's and also to determine gamma.
Yes.
The coefficient.
Yeah,
gamma.
but that's just the leading order.
Yeah.
I thought gamma 1 you got from the first equation.
But in terms of lambda.
But in terms of lambda.
In terms of lambda, but lambda was known.
No. I'm just putting in lambda here.
Wait. Isn't this lambda is not the critical lambda?
Right, but how do you know what it is without the epsilon?
Yeah.
Without
So I want to find the.
Okay, you don't want to use that.
Yeah, right.
Okay, I see.
I don't want to use the information that you get
yes.
from.
Okay, you don't want to use that.
Yes.
Then I could have the same question as you asked. Okay, so how do you get it?
So this I use this equation, right?
Yeah.
So that is 3 delta plus gamma 3 equal to 2 plus delta plus gamma 1, right? So 3 delta is 3 minus 3 epsilon by 2 plus y3 comma 1 times epsilon equal to 2 plus 1 minus epsilon by 2 plus y1 comma 1 times epsilon. Right? I'm just using this thing. So 3, 2, 1 cancels off.
So you've got two different relations for delta in terms of.
Yeah, that's why I said that this relation is going to be important. So then you get y3 comma 1 minus y1 comma 1 is equal to 1. And then you plug that in here. These things you already know. So the only thing you need to know is this comma 1.
It's very clever stuff.
Yeah. So this is what gamma 1 turns out to be. And then so after you know what gamma 1 is, you can actually start crunching out results for gamma 1 from this. Everything else follows from this equation. So that's it. So then you will have for gamma 1 equal to 0, which will actually tell you that phi I anomalous dimensions will start at least at order epsilon square, because y1 2 is the coefficient of epsilon square.
Now you should be able to see large n factorization here, right? You should be able to see that phi squared to the n at leading order in 1 by n has the same anomalous dimension as
n times the power n.
Yeah, a little n. Sorry, let's call it little n.
Yeah, so
Its anomalous dimension to leading order is
In gamma 1.
m gamma. Right?
yeah, so
M
you can
gamma.
actually do it from there. So you will take just p going to. So you will just take p going to sufficiently large, right?
I was thinking, no, p fixed but n going sufficiently. Oh, p is what?
No, p is
what I
n
call
going.
m.
P is what I call it, right? So I keep that fixed. So that should be fixed, but you take capital N going large.
So capital N going to large.
It's probably the fact that it's linear in P.
Yeah, exactly.
That At large n,
So it's just P. Right.
and that's probably right. It's P times gamma 2.
Yes.
So there's a P hanging around also in the middle.
But
But
we
n
take large
is much larger, right?
Anyway.
Yes.
Okay.
So that inside the brackets, the P does not play much role.
Yeah.
Yeah.
I mean, if the formulas are looking valid up to all n, then obviously it should work. So that's what Critical has done, and recently some so ICTS people and some from our department has also worked on this fermionic counterparts.
Who are the people?
So there is Kasi, who is sitting in the audience there, and Sudeep Amin from ICTS, and Rajesh Gupta, yes, they were also in, and one from our department is Avinash Raj.
Fermionic counterparts for the critical fermionic.
Yes, it's a critical cross-level model into the excellent dimensions. Yes. So, but again, the flaw is in here. I mean, the limitation here is that it just go up to the leading orders, not up to all orders, because the shortening condition or the equation of motion that you are using does not take into account the quantum corrected loops.
So you have been able to find the location of the Wilson-Fisher fixed point without using beta function equal to 0.
Yes.
But presumably somewhere conformal water identities have gone in.
Yeah.
So somewhere the information about 0 beta function is hidden.
Yes.
Because you have used conformal water identities. Because conformal water identities are finding you the location of the fixed point.
Yes, in some sense, yes. So it's like using one to find another, in the another implies the one you are finding.
All right.
Yeah, but this approach is a very elegant start.
Almost 30 years or almost 20 years back, this is what we have done.
Oh.
To find some conformal invariance condition by imposing TV equal to HV condition. This is of course for 3 quantums and more complicated.
Yeah. Sorry, what is EV equal to?
I mean the order identity of
Okay.
operator product expansion
Yeah.
of primary fields. So you
Yes.
say that I want to locate the coupling constant so that the this condition is satisfied. The T O equal to H O divided by Z minus W whole square. This is satisfied.
Yeah.
Then you get junk terms on the right hand side, okay, which are not part of this OP.
Okay, and
Then
you get constraints from that.
You put that junk equal to 0. That turns out to be the same as the beta function equal to 0.
Nice. Oh, so that junk, I mean, the extra terms that you are getting is actually providing you with the constraints.
That turned out to be the same as the beta function equation.
Okay, so this is what was there in their story. And then, so this is just a flash of what people are doing right now using this numerical bootstrap approach. So what they're again considering is some point model and using the conformal bootstrap equation. So suppose this is the S channel, the left hand side, which is connected by crossing. So by crossing, I mean you take pairs of OPs in this 4-point function. So this is one pair of OP between phi I, phi j, and phi k, phi l. And then you have another pair of OP between the interchanged counterparts. So crossing symmetry will tell you that there are lots of these functional constraint equations. These T, ST, and A actually signify the symmetric traceless and antisymmetric parts, because it's a Neumann vector model. Antisymmetric parts also are there, right? So spin 1 current, spin 3, and so on. And then there is you have a set of functional constraints, and then you can put in things in whatever code that you have, some very huge numerical code that people use globally, and then you can find some numerical results to match with whatever exists for, say, some real-time systems like liquid helium 3 and so on.
So are we supposed to understand those equations? What is P? What is G? G
So
blocks?
yes. So G has a conformal block. Sorry, not been clear about it. So you write down phi I, phi j, phi k, phi l. You can write down in terms of the tensor structure that is denoted by ijkl for the trace part times conformal block times this is OP coefficient square. times the G delta comma L, which is the conformal block for the 4-point function. And then we have another tensor index, which is PIJKL, times another of this kind of fellow, plus this AIJKL, times another of this kind of fellow.
Clear.
Right? And then on two sides you have related to each other by cross symmetry, and finally you end up getting three different sets of equations that you should solve consistently.
And with positive values.
Yes. This constraint that it appears is very important when you're putting things in a code. So the recent papers of Poland, David Simmons, Duffin, and all the other fellows, Philip Koss is also there, and Alessandro Ricci. So they have found that whatever was available from experiments are actually in close agreements with whatever they are finding from this numerical bootstrap. And this is a completely non-particular way of doing it. There is no epsilon, there is nothing. You just impose consistency and grind out the results. So this is one thing. But what we were trying to do is to use what Polyakov has done, and with the fact that Polyakov's paper is almost impossible to read and decipher, it's taking us some time.
But Polyakov student is one of your potential collaborators.
Yes, but I think this is the word coming from Polyakov student himself. So I'm just quoting you. So he used to utter this sometimes like that.
His papers in Polyakov suffer from the same.
Actually, he's not Polyakov student.
You're a camera.
Technically speaking, he's not Polyakov student. Yeah. So he's PhDs in real and function analysis. Yeah.
I was with him in college while he was a student, and we always thought he was Polyakov.
Okay, so what Polyakov will tell you is that you consider time-ordered correlators to start with, and then you will have some discontinuous part of the 4-point function. So the physical singularities that will come from considering the time-ordered 4-point function, the time-ordered correlations.
Now you're going away from Euclidean space?
Yes, I'm in Lorentzian space.
That's important for you?
Yes, little bit. Yes. So that's because that's why the time-ordered thing actually comes into order. Otherwise, in Euclidean space, it's just like Weizmann function. So you don't need time ordering.
This is not the 1974 paper where
1973, yes.
discusses
Yes.
I mean, the consequences of conformal invariance.
Yeah, so the thing is, what is the paper? And I have this paper with me. So it's non-Hamiltonian approach to conformal quantum field theory. And it's 1974, January. So you consider the time-ordered 4-point function for one vector models, and then you consider the case where the intermediate states actually go on shell, such that the 4-point function develops a discontinuity. So pictorially speaking, this is like that. So I'll just focus on the discontinuous part of the 4-point function since I'm considering on-shell exchanges. And of course, the discontinuous part of this 4-point function factorizes. So that's his idea. That's actually a proven fact. So there are theorems by Ullmann and Gu and Eden and Landshop where they actually tell you that this is actually what happens if you are talking about physical region singularities of this 4-point function. Yeah. So you're taking this time-ordered correlator. This is your 4-point function. I will give it as an index. And then actually I'm considering the discontinuous part in Q, which is the exchange operator there of this time-ordered correlator. And for the physical singularities, this discontinuous part factorizes and can be put into a form which looks like some 3-point function, phi phi O, where O is the exchange operator. Then there is an imaginary part of the propagator for O, and then there is another 3-point function which is phi phi.
So this is, you have used conformal invariance here.
Conformal invariance for this phi phi, the 3-point function. And this imaginary part actually comes from optical theory. So in the discontinuous part, it factorizes in the following way. is the
Sorry, this O is the thing that's running on.
yeah. So this is the O. Yeah. So
Ah.
this is some operator that is getting exchanged.
So and for the discontinuity of that, you use what you use the 2-point prime order 2-point function.
Yes. That's right. So D of Q is actually in the momentum.
So this looks very much like a unitarity equation.
Yes, exactly.
Yeah.
So unitarity is actually inbuilt in this.
Except I normally think of these equations as equations of scattering amplitudes and non-conformal. And you're telling me that there is a similar equation for operator product expansions in conformal.
That's the constraint that he will use at the last step. Right now, what he's using is just the conformal invariance of the 3-point, the vertex.
Wait, no, but what this equation, that diagram, just tell me where that equation comes from. Is this the OP? Is this the same as the OP? No.
Well, so in the momentum space, if you write down this, so you will get some things from here. I haven't imposed the OP at this point. I've just
What is that equation? Are you saying you're going to show us where that equation comes from, or you're going to use that equation?
I'm going to use that equation.
So then just give us a better sense of that equation. Is this an analytic continuation to Lorentzian space of the OP? It looks very much like an OP, right?
Yeah, and so when I'm using
Except
the 3-point
that
function,
discontinuity. So the OP
Yes.
doesn't have any discontinuity.
but the discontinuity is actually showing up in the intermediate states, not in the 3-point function.
I think he's taken the imaginary part
Yes.
of the OP equation. Is that what you're doing?
But the imaginary part is actually inbuilt in the propagator. So apart from this, so if you're taking this discontinuous part of the 4-point function, then if you are taking the imaginary part in the
Wait, just to understand, is there more information in what you're saying here than the OP? Or can you derive what you're saying here from it? Well, is this distinct somehow?
Yeah, so actually it has some more information than the OP, in the sense that once you get this discontinuous part and then get the full 4-point function.
I'm actually very confused. I thought that the Euclidean theory was completely fixed by OP kind of stuff.
Right.
And then once you know the Euclidean theory, you can get the Lorentzian theory
By analytical continuation.
So it would surprise me if that there's some new physical input that doesn't, in some sense, follow from it. But I might be wrong.
So the thing that I'm trying to say is following. So this is the discontinuous part that it factorizes in the form, right? And now your question is that does it have any more?
First, I'd like to see why this is true, and secondly, whether it's derivable from what you know Euclidean and analytical continuation.
So you're telling me whether I can use the Euclidean OP and then derive this?
Yeah, there are some fixed rules for how to get to the Lorentzian correlators.
Yes.
You know, Euclidean correlators well defined. Then when you try to continue, you Lorentzian space that goes across branches.
Yes.
And to time order, you have to do it in some particular way.
Yes.
And what is that? I don't know. I'm sure that you that carefully. Yes, okay.
So offhand, I'm not sure that I can show this right now.
Sure.
But I think we should discuss about this after this. But to answer one of the part of your question, this way of constructing this discontinuous part of the 4-point function in terms of this imaginary part of the propagator will actually give you some more information than the OPE. And the more information that it gives you is actually about this anomalous dimensions of certain operators up to subleading orders in epsilon. That's what we found as an exercise.
So it may be more useful somehow.
Yes. So I think it's related to the, I don't know if it's related to the fact, but Gautam was telling that if you use the conformal word identities, then you are getting some junk material on one of the sides, maybe on the right hand side. And those junk material comes with certain coefficients that when you impose some conditions on those coefficients turned out to be the fact that the beta function actually goes to 0. So here also we will get some additional pieces, just not the OPE.
But somehow we find it better to work in Lorentzian space than Euclidean space.
Yeah.
Even though we have very good evidence that Euclidean space is completely indeterminate.
Yes, and then you will ask the thing that about this analytic continuation with the Lorentzian
Anyway,
space.
yeah.
So we are starting off with the Lorentzian space for the time, and what we wanted to see that, I mean, yeah, we wanted to see whether Polyakov's method actually works or not, and it works to what order it works, and we're still trying to understand why it works. With Shiraz's questions of that. So anyway,
I think Kallol has a question.
Okay, yes. Can I hear it from here?
Yeah,
We can take it.
Sure.
Is O just a primary or any operator? It's also descendant.
Sorry, I didn't hear.
Is O a primary operator or is it used some of a descendant?
Yeah, so O is just a primary operator. So I'll show it to you what O is. I'll show it to you what O is. Can you hear me?
Yeah.
Yes, we can hear you.
Okay. So so the discontinuous part is by construction unitary, and we will also include the other channels. So basically we will use the ST and U channels to make it crossing symmetric. That's one point. And second is that this is the question that Bangalore has asked. So for this time I will assume that there are only two kinds of operators. So one of them is the phi square, and then another one is the symmetric traceless part. Both of them are scalars, but in the ON they are like I equal to 0 scalar and I equal to 2 scalar. Not sure. So that's what I'll assume for now. And obviously I'm leaving out a large part of the spectrum with the higher spin operators and so on and so forth. But I just want to see where this thing is going, just by assuming the minimalistic set of operators to do that. So now in the momentum space, the 3-point functions can be written in terms of these functions. So basically these have, well, in conformal bootstrap, these have named like this is the shadow part, this is the conformal block part of the 3-point function which gives the conformal block, and this is the shadow part of the conformal block. But anyway, we won't be doing it here. And we will be actually interested in taking this part. So so let me just draw a little bit of diagrams.
Actually, I don't even know what this is. What is N? What is T?
Yeah, I just read it. So so this is phi O in position space, right? So this is phi I, phi j, and O, and this has this I used the conformal invariant 3-point function, which is phi of x minus y to the power delta minus e, and then there is y minus z e, and then there is x minus z, and then I'm Fourier transforming this part. So d4 of so one of the things that I considered at some 0, so I will take this as 0. Yeah, so this as 0, so I have to consider d4x, d4y, exponential I x plus I cube y. So the momentum space 3-point function that I've written is just the Fourier transform of the conformal invariant 3-point function, and then we will say that so this can be given in terms of a normalization constant delta comma a times a function p a minus delta. So a is in my case equal to the dimension of space-time, which is 4 minus epsilon dimensions, and so I am doing this integral in 4 minus epsilon dimensions and so on. So basically I do this integral in a dimensions. So that's just taking the Fourier transform of the position space 3-point function, and this will be given in terms of p comma q, and there will be another part which will be L delta, then A is the space-time dimension, and then there is the function T comma Q, and Q to the power O delta minus A. This T comma Q has some integral representation in terms of the in terms of the hypergeometric functions, which looks like T delta comma A. So actually.
So what is the separation? What was the first? So I understand your Fourier transform. Now what is the first term you can know?
So this is the Fourier when you Fourier transform this, it separates out into two terms. One of them which looks like this, and one of them which looks like that.
Just the separation is by hand.
Yes. I mean, yeah, so I'm just taking two, so there is this term plus this term, so I'm just taking this term to be this, and that term to be that.
And there's some physical interpretation of these two?
Yeah, so the physical interpretation of that was what I was saying, that this part actually gives you the, when you are considering the conformal block, right, from sandwiching two 3-point functions. Although I would use the notion of conformal blocks, but since you wanted a physical interpretation, since I'm using this to sandwiching two 3-point functions, I'm supposed to get conformal block as it stands, and then there is a shadow part, so which is called the GS, and this is given by d minus delta comma l, u comma, and by using this method like monochromy and all, we just throw the shadow part.
You don't know this better time.
Yeah, so this is like taking, I mean, the 3-point function separating out into two distinct functional forms is actually the physical interpretation is given if you consider the 4-point function out of these two different contributions. So one of them is the conformal block as it stands, and then the another one is the shadow part which will throw in. That's what is the generic approach, conformal, some other function like lambda. And these functions are also have p, q, and so on defined in them, which is also comma q, and the integral of lambda is from 0 to 1. So that's roughly the functional form of the PDT form. And it also has a closed form expression, but we won't be needing that. The idea is that we will take this part, since the imaginary of Q. So the diagram I was trying to draw is the following. So what they will, so Polyakov's approach, if I take then the 3-point function. So suppose if I take the discontinuous part of the 4-point function, and Polyakov says that it's like 3-point function times the imaginary part of the propagator times another 3-point function. That's it. But if you transform just the phi 3-point function, what we are getting can be put into something which looks like just this part. So this is the propagator of the exchange operator, which is given by the exchange part of the propagator is given by imaginary of d of q squared is equal to q squared to the power delta minus k by c. And that's precisely the form that we are finding. So this is q to the power 2 delta minus k.
I have not understood what you've got this equation. Then what do you say about phi phi o?
So I'm just saying that when you transform the position space representation of the 3-point function,
Yes.
conformal linear 3-point function,
Yes.
you go to the momentum space,
Yes.
and in the momentum space, this function, this thing,
Okay.
this entire thing looks like the momentum space dependence of this 3-point function times the imaginary part of the.
There's no reason for that to happen. That's just coincidence.
Yeah, so that's the.
Well, you're supposed to put phi phi o, and in.
Yes.
And in whatever. O.
Right. But what Polyakov is doing is that he's trying to identify this phi o from that piece, which has this imaginary of d part.
This I just haven't understood. Well, you have a clear formula.
Yes.
Why are you using that whole formula? Why do you take some part
You
of
can use the whole formula,
Okay.
but then you will get the another one part which looks like some function of fu comma v. Sorry, not fu comma v. So you will get some function f1 p comma p prime comma q. So I'm just using the diagram. I'm just using this diagram. This diagram. So it has 3 variables, right? So p, q, and p prime.
Yes.
Right? So I will just get some function which is p prime comma q. Then since there is a since the 3-point function has 2 parts, I will get another function. If p comma p prime comma.
Yes.
Right? Now one of these function will have the discontinuous part in it.
In fact, why would you get 4? You get cross terms, right?
Yeah.
So you get basically 4 kinds of
Right. But then you can actually show that all the 4 terms are not independent.
Okay.
Actually, that is the part that we are actually trying to understand in the second part of the paper that we have Polyakov second part of the paper.
Okay.
So I'm a bit confused now.
Yeah.
So we begin with let's say the analytic continuation of the usual S-channel factorization or something.
Yes, yes.
And then you take the discontinuity of that, and you're saying that the contribution to the discontinuity comes from the discontinuity of the 3-point function phi phi o. Is that right? I mean, normally in a unitarity equation, what would have happened is that this stuff in the middle, it would be some 1 over t square minus m square minus I epsilon.
Right.
You take the imaginary part of that,
Yes.
and that gives you some discontinuity.
Yes.
Okay, that gives you delta of whatever, that makes it into an on-shell stuff.
Right.
Now, of course, a very complicated conformal field theory operator is propagating in the middle. It doesn't have that structure of 1 over p square minus m square minus.
Well, it does not have m square, but
it has some power.
Yeah.
P to some power.
Yes.
It has p to the some power. Okay.
Yeah.
And it has that power will generically have a branch. Either P to some power or P to some power times the log of P.
Good.
Yeah. So that
Always
is
have a
the
branch.
yes. Yes.
That's your in.
Yes. Yes. Yes.
That's it. So now,
Yes.
why are the phi phi O's playing a role?
Yeah,
By
but this is everything in 5. Yeah, exactly.
Yeah.
I have the same question.
Yeah.
So,
Why is something being special rather than?
no, I'm just saying that if you I think I'm not being clear. So I'm just saying that if you consider the phi phi o in momentum space, right, by Fourier transforming the phi phi o from the position space, you will get two contributions.
You have two contributions.
Yes.
And you're choosing one of the two for some reason. And we're not
Yeah, so
understanding why.
I'm just trying to identify which part of the phi phi o in the momentum space is giving me the discontinuous part.
But as Gautam was saying, the discontinuity was on if you go
D
back
of
on
Q, I thought it was
sure. The discontinuity was D of Q, right?
Right.
So there was no relation. I mean, everything in phi phi o contributes.
Yeah, so okay, so let me just
Discontinuity, I mean, on left hand side, you've got some, this is what you want to calculate. You're using the right hand side to calculate.
right.
The right hand side is a formula. The in was the discontinuity.
Right.
And the other stuff you have to put everything in, right?
Yeah, but so this is the thing that phi o, right, in position space. Let me just see is equal to the, so if you do that the Fourier transform, then it becomes some part of phi o.
Okay, let's say 1 plus 2.
Yeah, so this is
Term 1 plus term 2. When you're ignoring term 1, why?
Yeah, so and then it is giving me this so phi o times imaginary o.
No, this is the thing we're not understanding. That imaginary v was supposed to be put in addition to phi phi, right?
Right.
It should have come from phi phi.
Yep.
maybe he's saying that even the phi phi o
Has an
viewed in the Q plane,
Yes.
it has some branch cuts as well.
But his formula is not asking us to treat those as special.
That's true. How do you, yes, exactly.
He's saying the branch cut is in that in D,
Yeah.
and then whatever appears in phi phi o should go. So either the formula is wrong or
So basically, whatever the thing is that in momentum space, so you have P, Q minus P, and then Q. You have so that is the Fourier transform of this into the momentum space, right?
Okay, great. Let's say we accept that you get this structure. Now what? So firstly, should we have expected that in D? That in D in that formula was independent of the phi phi o, right?
So that's what I'm trying to say, that in the momentum space representation, this whole part comes as this phi phi o 2 times MD in the momentum space representation.
Yes, it's 1 plus 2, whole thing multiplied by MD, right?
No, it's not whole thing. It's this part plus this part multiplied by MD.
Is it sort of like having stripped off the propagator or not stripped off the propagator? Is that what's going?
I think so. I mean, yeah, it's like stripping the part from the 3-point function.
I think I know what you mean. I think I know. You see, suppose we were doing this with just free fields. The thing that would have come there would not be the full 3-point function, would be the structure function.
Yes.
But if you complete with the 3-point function, that is structure function times 3 propagators.
Okay.
Okay? So, suppose you actually use the full 3-point function. Okay? Then,
Oh, I see. So you're saying there could be additional singularities coming from the external legs?
exactly, that
Which is what I should
which normally you would just strip away. But he's saying that what you actually compute computed is a 3-point function times this other 2-point function. That's like a propagator.
Yeah.
You see, that is what you actually computed.
Right. So that is this part of the.
And then what are you going to do for the last 5?
So that's what. So if you just take the 3-point function in the way
you just put that other coefficient again.
Exactly. So that other coefficient
it's just stripping it off, stripping off the propagator. Okay.
Delta P comma P.
Yeah. So this term was a part that had no, whose residue killed the propagator.
Yes. Sorry, I'm not being that clear. Yeah.
Nice.
Yeah. No, it's clear. Nice.
So, and finally, we will consider 2 distinct limits because we are going to consider the full 4-point function to the dispersion relation, and this will be important these limits will be important when you're calculating the dispersion relation for this calculate the full 4-point function. So that is the discontinuous part in the Q plane.
Why didn't the first term have this Q before?
Why doesn't the first term have? That comes from the, if you Fourier transform. So there are 2 distinct terms. So this is function 1 times function 2.
No, but I thought in terms of Feynman diagram, it's just a leg, right? This Q is a leg, right?
Yeah, so Q is so one of the Q is the leg, and the other Q that comes with the power is the propagator that is being exchanged.
What is A?
A is the space-time dimension. So Polyakov uses not D but A, and he uses D as the conformal dimension of the.
Why did the first term have also the same propagator?
It's somehow that the numerator. Suppose you had a 1 over p squared minus n squared times a residue, times a factor. There could be a term in that factor that also has a p squared minus n squared.
Not PQ.
I'll give you an analogy. Okay, it's category amplitudes. You could have a term which is p squared minus n squared divided by p squared minus n squared. That would be sort of like a contact interaction, not a propagator going on. Okay, and then you could have a term where the thing is actually propagated. So that's the analog of that first piece. For him, it's trivial because it does not have this. It doesn't have the discontinuity.
Yes.
It's sort of like a contact interaction in unitarity equations. Okay, it just doesn't enter the unitarity equation, and that is clearly just the Q to the 2 delta minus A is just the propagator of an operator whose space dimension, whose ordinary dimension is delta.
Yes.
That's just the Fourier transform.
Yes.
And it's clear once you say it now that if we were doing just ordinary scattering, once again the 3-point function we would calculate would have the 3 propagators.
Right.
So it's not that 3-point function that appears in the unitarity equations. Once you strip off the propagator.
So just put Shiraz on this like stripping off the propagator part of the 3-point function in this.
And of course you could ask, should we strip off the external propagators also? But who cares? Either you do them all or you don't do them. This one that's running in the middle.
Sorry, what do you mean by stripping off the external propagators?
Meaning when you compute this thing,
yes,
the thing that you have will have external propagators coming
as
well.
Yes.
But okay, you don't care.
Yeah. Okay.
You're just equating this.
So once you have fixed the form of this in terms of the functions with some limits, then the next step is to find the full correlator by using the dispersion relation that we have here. The discontinuous part of the 4-point function. Sorry, there should be a time ordering. I've missed that. Discontinuous part in the Q plane, and finally we'll take the Fourier transform of this full 4-point function. That's it. So after you take the full Fourier transform of this full 4-point function, you will get some position space representation in terms of there are some parts in this amplitude that appear. So AI is the coefficient for, so there are 2 operators, right? So one of them is O1, O0, which is phi I, and another one is O2, which is this estimate contribution minus 2 by n. So this I is equal to 0 for this one, I is equal to 2 for that one. So in this 4-point function, there is also a contribution from the T and the U channel, and because I've incorporated all the S, T, and U contributions in the 4-point function.
So the discontinuity you compute from your formula, right?
Yes.
You compute from that.
Yes.
By taking that
Yes, and then I will just identify the part which will take t delta. That's it.
Right.
And then I will take the dispersion relation, find the full 4-point function, and so in this full 4-point function there is also a contribution from the 3 channels, S, T, and Q. So that's
Put that in by hand.
yeah. I made the but I did not. Polyakov made this in process symmetry, but taking into account contribution for this.
But in ordinary OPs, if you sum everything in one channel, you automatically get everything in the other channel. You don't put both in.
Yeah, but I don't think he's putting in the OP constraint at this point. He's just trying to put
it for the imaginary paths.
Yes. Yeah. So.
No, but are you sort of focusing on a particular channel? On a particular intermediate state or what?
Well, I'm just focusing.
You have the sum. You have the sum over all possible operators going.
No. I have only 2 operators in the spectrum, right? For consistency.
Okay. So you have OPs clicking only with.
Yeah. So this is for So this is an assumption. Obviously, this assumption breaks down after some particular order range.
But it's the summing over channels an approximation? Or suppose you have summed over all channels, all operators in the S channel, we will then also have to check sum over operators in the T and U channel?
You are saying that, say for example, I did not take the scalar, but all the other things.
Suppose
all spins and all, right?
Yeah, suppose you could somehow do it. I just want to understand whether this is, because in the OP that would be the wrong thing.
Yes.
So if this comes from the OP, I would suspect that would not be right, or it might be right in an approximation where you keep some low. You say because low-lying operators in one channel are very high-dimension operators in the other channel.
Yeah, so you're considering this.
So it could be that this is a reasonable approximation. You symmetrize by hand, very easily.
Yeah, so in the other 2 channels, there is only one part. So when you're calculating the Fourier transform, so for example, when you're calculating the full 4-point function from the dispersion relation, it appears that the T and the U channels actually contribute in very high energies, not the low ones.
That's the usual state.
Yes,
right?
Yes, that's what happens here as well.
So you are again taking some large spin or large twist?
No.
Then how? What is the approximation?
So the approximation is that, so suppose you are considering the this is in the, so this dispersion relation, right?
This is like an optical theory, right?
Yeah.
You have the imaginary part,
right?
And then you do this.
Yeah. So you get the full 4-point function.
Yes.
But you computed the discontinuity in some approximation, and Gautam wants to know in what approximation.
Yeah. So I'm calculating the
So we know what you've done.
Yeah.
But in what limit? What justifies? Is there a systematic parameter that would make this exact?
So the dispersion relation is calculated in the regime where there is so I'll just draw the diagram once so that so P Q minus P Q prime Q minus P. So the approximation for this dispersion relation is that P is much less than P prime P is much bigger than P prime much bigger than P. See this regime that I am considering the dispersion relation.
So low energy exchange.
Yes, and then like you said that in the other channels, the high energy exchanges will be dominant, right? So that you can see so this is the S channel, right? If you can consider the D channel, that will be, so this will be Q minus P, Q minus P prime, P minus P prime, P and P prime, right?
Yes.
So in that case, you will see that only in the only one part of the the discontinuous part one part of the dispersion relation actually contributes in both the T and the U channels.
Wait, but just in position space, are you considering the limit when you take 2 operators here?
Yes, that's right. So in momentum space taking, this is actually equivalent to the fact that R prime. So you will have, so let me just write down the 4-point function here in position space constant. So you will, in position space you have phi I of R, phi j of 0, phi k of R, phi L of R plus R prime, right? And then you are taking the limit where R comma R prime is much less than R.
Correct.
So you have 2 operators here, then separated by a very large distance, and then 2 operators here.
Yeah, so in that limit, of course, the lightest operator exchanged off.
Yes, yes.
But you're saying you have to take the cross channels into account as well.
Yeah, so cross channels, but in some specific part
For
of
something
the
particular, you tell that.
Yes.
Okay.
Why did you take P much bigger than P prime?
Why didn't I take?
Why did you take?
Oh, so yeah, so the P much bigger than P prime actually comes in this part. So when I'm considering the so this is your so then there is incremental part, then right. So that is the part, and then your yeah. So this is actually an assumption which justifies the fact that r comma r prime is much less than r. Although
No, I think the Ronald's question is that if you take P and P prime both comparable, but the other one
yeah,
much
that's what I'm saying.
much smaller,
Much smaller.
that would do this. I think it's right.
Yeah. So this in real space R much less than R prime is much less than R.
Yeah, already also
Yeah.
bunching
And
bunching
for
of
the
two operators.
Yeah, that's correct.
bigger issue is that to get you're using P much bigger than P prime really important in the T channel.
Yeah, so
Yeah,
that's what I was trying to say that through the dispersion relation that this part is actually important. If you take P and P prime both comparable, then the exchange will have a smaller.
Okay, so you're saying there's a small clump here, a bigger clump here,
Yes.
and they're separated by some huge distance.
Yes.
You can do that.
Yeah. So why is it-
Why?
Yeah. So this is another approximation that I'm still trying to get my hands on.
Somehow it's convenient.
Yeah, somehow it's convenient, but I agree with your question that even taking insofar as this limit is concerned, P comma P prime taking comparable to each other should also work. Although
You know, I have some. Okay, so
Yes,
please,
yeah.
okay. I have some other. I mean, earlier in your large spin studies and
Yeah.
stuff, there you choose the operators phi I, phi j, phi k, phi l, etc., such that though the choice of those operators itself sort of pushed effectively pushed you to some corner of this UV square, whatever. You know,
Yeah,
I mean,
yes.
it is now
in the light
it
cone,
seems-
in the light cone.
now it seems that it gives you limited information about a generic operator.
Yes.
Rather than, wouldn't you like to derive the 4-point function exactly with some specific choice of I, J, K, L, and these operators as you have done before? Or that's not what you're doing. I'm saying now it is giving you some limited amount of phase space. I mean, right? This R prime. Must
Yes, but that also corresponds to, in some sense, the light cone limit. Because if you consider the conformal cross ratios in this limit, you will see that U actually tends to 0, and V actually is just little bit less than 1, or actually tends to 1.
So okay, so that your goal here is to get the 4-point function in that sort of limit.
Yeah. So the way the limits were chosen through the momentum space definition actually makes it very evident that you are actually in the light cone limit. Because in this 4-point function, you can just take the u's and v's, and then you will see that in this choice, where this r comma r prime is much less than r, capital R, this actually forces one of the conformal cross ratios, specifically u, to go to 0. So this choice actually, forces the condition that will have this thing. So in the momentum space, the thing was that if you take P and P prime, you comparably will also have this low energy scatterings there. And I think this neglecting the low energy scattering was a pretty important.
So you're saying that this particular limit is the one that acts as the duality between S and P channels.
Yeah. Okay, that's right. But insofar as r comma r prime, this limit is concerned, I think Shear is right that even P and P prime both comparable to each other will also do this thing. Yeah. So this is one thing. So after you have done this, taken these exchanges in this particular limit that V is much bigger than P prime, much bigger than Q with your account, then you will get the full 4-point function in momentum space, and finally you Fourier transform it to position space to get some dependence on this small r prime and capital R square. And this delta I is the anomalous dimension, the conformal dimension for the exchange operator. So I'll let me phi I or the symmetry trace combination. So now what we have done is the fact that there is
who has done?
Polyakov. Yes. We are just following for this time at least, trying to understand what he's doing. So yes, now you can consider the OPE of these two and then these two, and then you can form the algebraic part. So this is what you will call the algebraic correlator. The other one was the unitary correlator, and this algebraic correlator. This is not very difficult to show that it breaks up into two different contributions, one for the trace part and one for the symmetric traceless part with some specific forms. And the idea is to determine this h0 square, f2 square, plus the anomalous dimension of this delta 2, and if possible delta 5. Delta 2 and delta naught, and if possible delta 5. So, like I said, the delta 2 naught and delta 2 are the dimensions of the exchange operators, O0 and O2. And then what you will do is that you will take the unitarity part.
So I didn't understand
Yes.
the algebraic part. What algebraic part is just ordinary OP?
Yeah. So it is just taking the OPE and then taking the 4-point function from that OPE.
Now you are trying to get consistency between OP and what you said.
Yes. So that was the idea. So now you will take the unitary correlator and transform it back into the position space. The last part is actually the discontinuous part that we are transforming back into position space, and the first part gives you the disconnected parts of the diagram. And then you have two different contributions, one for the phi scalar and one for the symmetric traceless part. And these two contributions are they are broken up similarly based on the symmetry structures. I know specifically of these forms since these are built from the momentum space. And finally, we will get some additional coefficients apart from the OP, which looks like this part, this R to the power minus 4 delta phi, and then there is a log term in that. So that these extra parts come from the momentum space.
Kallol, sorry. I know it's completely not your fault.
Yeah.
Because we've been stopping you every 30
that's
seconds.
fine.
But we'll miss lunch unless we stop in 15 minutes.
Yeah, and I think it won't take more than 15 minutes.
Yeah.
So after you solve all this, you will get these two. So I will just do an epsilon expansion of the intermediate exchanges, and then the external legs. So this is an input. We could not determine the order epsilon square anomalous dimension for the delta phi. This is impossible to do using this correlator. So this is an input, and once we put in the input, we will get that the anomalous dimension up to order epsilon square is completely consistent with what happens from the diagrammatic approach, even at finite time.
Now this went a little fast for me.
Yeah.
I know you're running out of time, but just is this? You say you have two different expansions of the same code.
Yes.
One from this unitarity sort of approach, which I only half understand, but you explain, and the other is just the ordinary OP.
Yes.
And just by demanding consistency of the two, you get something.
Yes, that's right.
So unitarity is giving you an equation rather than inequality.
Yes.
That's a special thing. Ordinarily in the bootstrap approach, unitarity gives you an inequality.
Yes.
Here is somehow giving you an equation.
Equality, yes. So it is giving you, so you were asking that, are you matching it with the OPE?
Yeah.
Are you getting some extra information? So the extra information is hidden in this this additional terms, something like jump, and then I'm putting all of this to be zero. The coefficients of this.
Was these other cross channel stuff somehow very important?
Yes. They will contribute to this last term.
So then I have a conjecture. My conjecture is that what you're doing is the OP, but also somehow summarizing the effect. That the other thing is somehow summarizing the effect, a particular effect of exchange of very high dimension.
Yes. I mean, you are saying the T and the U channel.
Yes.
Right?
Yes.
Yeah.
So that is a new thing from the point of view of the OP.
Right. So, and that's what I was trying to say, that this limit, this high energy exchange, which is inputted through this operator, that is why he had to choose this limit.
Right.
That P is much bigger than P prime. Otherwise, the T will also contribute to this S and the low energy part of it.
This I didn't get what you have understood.
I didn't understand. But let me just say,
Yes.
you see, if you do systematic OP in Euclidean space, there's one very natural thing to do, which is expand in dimension. As you take two guys here, two guys there, very far away, that's a systematic expansion. However, we already know that the OP, that the crossing symmetry gives us more constraints than that. Because we know that just low dimension operators in each channel dominate their channels. And we also know that low dimension operators in one channel summarizes some information about the running of very high dimension operators in the other channel. So my guess, which is probably wrong, is that the new information that's put in on the other side summarizes not just the information of the propagation of low dimension operators, but some part of the information of propagation of very high dimension operators, which is nonetheless determined by the low energy spectrum. Somehow in some very clever way.
It's even like open closed modular APIs.
It actually sounds very much like what you need to do to improve Maldasena's causality.
You mean this is graviton 3-point vertex frequent?
We can talk about it.
Yeah. So this is as much as surprising for us as it to this is much surprising for us, yes. And because of this agreement
Because of this agreement, we believe that Polyakov was not full of shit.
No, I wouldn't say that, but we are not expecting. Let's pretend that. Let's pretend the fact that we are not expecting this. So agrees with everything that we have. One of the questions that we had is why agree at the order of epsilon squared, because that's what we would expect, that the higher spin contributions and these operators that we left out will contribute at least this order, but it didn't. So one guess that we can take, one guess that I have is that they have the OP for the higher scalars themselves are some higher order than epsilon, and so are for the higher spin operators. That might be one of the reasons, but we still don't know whether that's true or not. But that's one of the that might be one of the reasons that it did not compute at order epsilon squared, because OPs are themselves higher than epsilon, so for higher spin operators and so on. But one check that this is just a small exercise that we did, is how much of this light cone limit of the bootstrap that you were asking is it consistent with the epsilon expansion? Is it not? How much of it is that consistent? And so, for example, if I consider this n equal to 0, the 0 twist and high spin operator, and consider the fact that this delta phi has some anomalous dimension and so on, and then again on top of that I consider that phi square has a dominant exchange. This is an exercise. We don't know whether it's completely generalized or not. Then we see from either our results n equal to 0 or the results from Kaplan that it agrees with the larger part of what Wilson and Covert had for these higher spin operators.
L is the spin?
Yes, L is the spin, and this factor of 9 is very crucial that comes from just this consideration, by considering delta phi, the phi square as a dominant exchange. But again, we are not even close to calling this a conclusion, because this is just an observation. So this matches with Wilson and Covert for large spin. That is one observation we had. And finally, we wanted to see if you can actually get the anomalous dimension of the external phi operators by considering any other correlator, not just the 4 phis. And for that, we considered the 4-point function of two different operators, which is phi I and phi squared phi I. But here also, so the next steps are whatever I was trying to explain. First, you consider the unitary correlator, then the algebraic correlator, and then you match with each other. But this also, which was, first of all, it was very tedious, and second of all, we could only fix the leading order from considering some double zeros or something. So this, I could not see why, how to proceed with this order epsilon squared term that we set out to calculate. We only could fix that, okay fine, this has anomalous dimension of order of coefficient 1 at order epsilon, and this is just 1 minus theta epsilon. That's it. So what we are trying to do is to understand Polyakov's paper from from a different point of view, which is the Mellin space.
This is your Penadona segment.
I guess. Yes. And the idea is to consider whatever Polyakov has done in terms of the the projection operators that leads up to forming the conformal blocks. Generically, it can be a spin object with there some spin projections. I keep spin here, but here I put scalars. Sorry. And then you consider it. You use whatever star-Simonsic formula, whatever you have to go to the Mellin space, and then you consider the unitary amplitude for using this conformal block in the Mellin space. This m nu is the spectral function. Again, I don't have any very good clear-cut idea about how to derive this in complete generality, but this is in connection with this bulk Witten diagrams that you can have. That's the closest that I've been so far. And finally, you take the crossing symmetric part, take the residues of this, and of course, again, for the epsilon square order, we could match the coefficients of this anomalous dimensions for phi square and for the symmetric crystals combination. But this is also very far from complete, so concluding remarks. Even if algebraic, the constraints that Polyakov has, a lot of them, I mean it's a very complex set of complicated equations, can be solved order by order, and it is more convenient than the bootstrap approach with functional constraints. It needs to be understood with operators for generic spin, and with much more detail with what is going on there. I will also include Shiraz's questions and your questions in that. But we can learn more about it, and it's still under admission.
The last part I haven't completely understood. Yeah. But you're using it order by order. But, yes. Are there equations that you think in principle determine the full solution?
I don't think that. Again, it's the Penedonist approach that thinks that. I mean, the first confusion is that I don't understand is why the spins should start contributing order by order in epsilon. It could be that there are some operators which contribute all of them at some same order in epsilon. I don't understand why this should be the case. And why is Polyakov so sure that you can take just I mean, you will get some Taylor series expansion. Exactly, right.
And what is the truncation?
Yes, exactly. I don't understand it.
But suppose you took all the contribution of everything.
Yes.
In principle.
Yes.
And then equated the two things.
Yes.
Do you think that gives you equations which may be hard to solve in practice, but in principle will determine the whole problem?
No, that also I haven't even clear-cut idea. The reason is the following. So when you are considering this, so Polyakov has emphasized extremely on this spectral function, right? The spectral, there is some kind of spectral function that is there in the 4-point correlator that he has managed to grind from somewhere, and he says it's very easy. But okay. So, but then he's saying the fact that for each spin, only that part of the unitary amplitude contributes. I don't see why the lower spin unitary amplitudes cannot contribute to the same order. So I honestly I don't know. Honestly, I don't know what.
Even I think it's unlikely because I really have the feeling that there should be nothing more than Euclidean space.
Yeah.
That in principle there's no information that's not contained in Euclidean space and reflection positivity.
Right.
That these, I mean, are there theorems that tell you that if you've got a Euclidean, you've got correlation functions of field theory in Euclidean space, and if it satisfies reasonable axioms, including reflection positivity, then you can always analytically
continue to the Lorentzian
to give you correlators that give you anything that you want
in a unitary thing.
Well, reflection positivity will ensure
unitarity,
causality, everything.
Right.
So there should be no more information in principle than this.
These two things that are being matched.
Yeah.
Why does it give? Why isn't an identity?
But it could be a rearrangement of the simulator. That's something that's not. Sorry, I think something that's very interesting about the OP and that is not much emphasized is the fact that the question of how much does the low energy spectrum determine. It seems to determine only things very far away, but there are also the cross channels. So it determines something about short distance behavior as well. And maybe this is an efficient way of extracting that thing. It's very vague.
No. But then, of course, but then I think Gautam was saying that you should not be getting any more.
In principle, I don't think you should have any more solvability in principle than if you just imposed all the Euclidean conditions. But maybe if you're approaching it from starting with the low energy spectrum, there is some consistency here because it's just some rearrangement of the information.
Yeah, but so then I will reverse the question around and I will say that if you include everything,
yeah.
So then shouldn't it be an identity?
Yeah, I think so. In fact, what I think would be really a really nice exercise is to prove Polyakov's equation.
Yeah.
By analytically continuing Euclidean. I think it should be possible.
Right.
Once you can do that, then you will have a clear understanding that there's no more information in principle.
Yes.
But then it may be a useful way of reorganizing.
Yeah.
But I think that sounds
that's
like a really good exercise.
Yeah, that's something. Yeah.
Okay, sorry, but let's ask for questions from Bangalore first.
Sure.
Oh, maybe we should clap first. Bangalore. Can you hear us, Bangalore?
Yeah.
Okay. No questions. No questions. No questions from Bangalore. More questions from Bombay?
Well, we have asked 100 questions.